Good morning students, welcome to video lecturing class on control engineering subject. So today we'll start with the fifth module, that is compensation of control systems. So basically all the control systems are designed to achieve the specific objectives. So the certain requirements are defined for the control system. A good control system has less error, good accuracy, good speed of response, good relative stability and damping, which will not cause undue overshoots and many more other reasons. So for satisfactory performance of the system, the gain is subject adjusted first. So in practice, the adjustment of gain alone cannot provide the satisfactory results. So this is because when gain is increased, the steady state behavior of the system improves but results into poor transient response, in some cases may even instability. So in such cases, it is necessary to redesign the entire system. Thus, the design of control systems is a challenging job. So practically, the design specifications are provided in terms of precise numerical values according to which the system is designed. So the set of such specifications include the peak overshoot, peak time, damping ratio, natural frequency of oscillations, error coefficients, gain margin and phase margin. So basically the system compensation, it is nothing but the adjustment of system to meet the required specifications by adding external devices to it. So the external device used for the adjusting the system to meet the required specification is called compensator. So the next question comes, why it is required? So the requirement of system compensation is, the first reason is to have the less error and to have the good accuracy. The second one is to have the good response speed, that is whatever the disturbance occurs or whatever the input you are going to give, it should respond in a very less time. Okay. Then the third one is to have the good damping, that is reducing the overshoot. So to have these things, gain is adjusted. Sometimes adjustment of the gain alone cannot provide these satisfactory results, because when gain is increased, the steady state response improves but the transient state response reduces. So to avoid this, the system can be adjusted to meet the requirements by using the external components called compensator. So there are some types of compensation is there. So the based on where the compensator is introduced in a system, there are three types of compensator. The first one is series compensation, parallel compensation, and third one is series parallel compensation. So the first one is series compensation. Another name for this one is cascade compensation. So in this, if the compensator is placed in series with the forward path of the transfer function of the system, then it is called as series compensation. So as you can see in the figure, the compensator is placed in a series with the transfer function of the system, where g of s is forward path transfer function and g suffix c of s is transfer function of the compensator. So in this type, the signal flow is from lower energy to higher energy level. So this requires additional amplifiers to increase the gain and to provide the isolation. The second one is the parallel compensation. The another name for this one is feedback compensation. So in some cases, feedback is taken from some internal element, not the total system feedback, and a compensator is introduced in such feedback path to provide the additional internal feedback loop. This is called as parallel compensation. So this is the figure for the block diagram for the parallel compensation. So the first one is the original system. When you add the compensator to that one, the second one is the block diagram for that. So here one thing you can note here, the internal feedback loop is feedback given to the single feedback signal. Then the third one is the series parallel compensation. So in some cases, it is necessary to provide both types of series as well as a parallel scheme. So this is shown in the figure. As you can see in the figure, the internal feedback loop. Okay. So that is the combination of the series parallel compensator. Then the next bit is the compensating network. So the compensator is a physical device. It may be an electrical network, mechanical unit, hydraulic, pneumatic, or a combination of various types of devices. The commonly used electrical networks are, the first one is the lead network, that is lead compensator, lag network or lag compensator, lag lead network or lag lead compensator. So the selection of compensator, that is choice of compensator, is based on, the first one is nature of the signals available, second one is power levels at various path points, third one is available components, economic considerations, and design experiences. Based on these 5 points, you have to select the proper compensator. In that, the first one is lead network or lead compensator. So this is the network diagram for that lead compensator. So when the sinusoidal signal is applied to a network and it produces a sinusoidal output, that is steady state output, having the phase lead with respect to input, then it is called as lead network. So consider an electrical network which is shown in the figure. So you apply the KCL, that is Kirchhoff's current law, at output node. So where we have I1 and ID as the I, that is when you apply the KCL to the network, so you can write it as C into D of EI minus E0 divided by dt plus 1 divided by R1 into EI minus E0 minus 1 divided by R2 into E0. Taking the Laplace transform of this equation, so it is a C into D of derivative is there. So whenever the derivative is there, when you take the Laplace, you have to write S there. So S into C into EI of S minus E0 of S plus 1 divided by R1 EI of S minus E0 of S is equal to 1 divided by R2 into E0 of S. So you simplify this equation to get the output by input equation, that is output is E0 of S, input is EI of S. So when you simplify that, you will get the last equation, that is E0 of S divided by EI of S equal to 1 divided by R1C plus S divided by R1 plus R2 divided by R1 into R2 into C plus S, which is equal to S plus 1 by T divided by S plus 1 divided by alpha T, where the T is R1 into C and alpha is R2 divided by R1 plus R2, and which should be always less than 1. So lead compensator has 0 at S equal to minus 1 by T and poles at when S equal to minus 1 divided by alpha T. So now look into the what are the effects of lead compensator. The first one is it increases the damping of the closed loop system. Second one is reduces the overshoots, rise time, settling time, thus improves the transient response. So that it will give the quick response. Third one is it improves the phase margin of the system. Fourth one is increases the bandwidth of the closed loop system. And fifth one is the steady state error doesn't get affected in this compensator. Then the second one is lag network, that is lag compensator. So if the steady state output has phase lag with respect to input, then the system is a lag compensator. That is, that steady state output should have the phase lag with respect to input. Then we can call it as lag compensator. So let us consider a network which is shown in the figure. So apply to this network the Kirchhoff's voltage law, that is KVL. So we'll get EI of t equal to I of t into R1 plus I of t into R2 plus 1 divided by C integral of I of t into dt. And for the second network, it is E0 of t equal to I of t into R2 plus 1 divided by C into I of t into dt. That is the second one. So taking the Laplace transform of equation number 1 and 2, you will get these two equations, that is 3 and 4. Now substituting this I of S in equation number 3, so that we will get E of S equal to E0 of S divided by R2 plus 1 divided by CS into R1 plus R2 plus 1 divided by CS. So when you simplify this equation for the output by input ratio, you will get E0 of S divided by E of S equal to 1 plus S into R2C divided by 1 plus R1 plus R2 into C of S. Now dividing the numerator by R2 into C and the denominator by R1 plus R2 into C, you will get the final transfer function, that is E naught of S divided by AI of S, as 1 divided by beta into S plus 1 by T divided by S plus 1 divided by beta T, where this T is R2 into C and beta is R1 plus R2 divided by R2, which is greater than 1. So now this lag network has a 0 at S equal to minus 1 by T and a pole at S equal to minus 1 divided by beta T. So now the effects of lag networks are, first one is it is a low pass filter, hence allows the high gain at low frequency. The second one is the bandwidth of the system reduces, response becomes slower here. The system becomes more sensitive to parameters variations. Fifth one is makes the system less stable, and sixth one is improves the steady state performances. Okay, so these are the three types of compensator, that is lead and lag, and the last one is the lag lead network, is the combination of lead and lag network systems, so that it will, the effect of that, the third compensator will be, it will give the quick response to the transient variations, and the steady state response will be less affected in the third type. Okay, so I will end the session here itself. So if you have any doubt, you can leave the comment in the comment box, and you just go through this video and go through the notes, so that you will get the idea of when to use the lead compensator or when to use the lag compensator. Try to understand the effect of the compensator. Okay, so if you have any doubt, you can leave the comment in the comment box. Thank you.